Um, and so one of the things that I wanted us to practice today is sense making is what I call it. Okay, so the instructor tip for this was that you can find y prime by implicit differentiation, and then you have to find ordered pairs of x and y. So like once you find the derivative, you can solve for x values that are critical values, where the first derivative is 0. That gives you potential locations or potential x coordinates for maxes and mins, right? But this isn't a function, so in order to find the corresponding y values, you have to plug back into the original equation and solve for y values. And you end up with like a whole bunch of values, right? So you have to keep track of the ordered pairs that you come up with. But I also, and this is not to discourage you from doing calculus, this is to encourage you to think, which is, so when you look at this problem and the equation itself, first and foremost, is this an equation that gives you a function of y in terms of x? If you solve for y, do you get a unique output for every input? Does that question make sense? So if I were to solve for y, I'd have y equals, so like I'd have y squared equals x squared minus x to the fourth. And then to solve for y, I have to take the square root, right? When you take the square root, you introduce a positive and a negative. So you end up with y equals plus or minus the square root of x squared minus x to the fourth. So you plug in an x value, you get out two y values, right? So that eliminates this as an answer choice because that's a functional relationship, right? So that gets us down to A and C. Again, I'm not showing you this to discourage calculus. I'm showing this to you to encourage critical thinking, okay? So what else could we do? So when I look at these two curves, right, there's some striking differences. In particular, there are 3 y-intercepts here, and there's only 1 y-intercept here. Plugging in x equals 0 is one of the easiest things you can do, right? So if you plug in x equals 0 into this equation, what do you get for y? 0. Do you get any other values? No. So that means that the graph should only have one ordered pair when x equals 0. That forces it to be this as an answer, right? So critical thinking, right? There are ways to explore graphs outside of calculus. But in order to do what we just did, what do you have to understand? You have to understand that points on a curve are the points whose coordinates satisfy the equation that you were given, right? If you don't understand that, then the conversation I just had doesn't mean anything, right? Because then, yeah, it wouldn't make any sense. So that's the key, though, is understanding that points on a curve are the points whose x and y coordinates satisfy the equation that's given. Okay. Adam, were you going to ask a question? Okay. Sure. Which one? Critical points. Yeah. So, right. So again, this is great. This is stuff that I want to talk about today. So, okay. So if you have the blue graph is the graph of the second derivative. The purple graph is the graph of the first derivative. If they're asking you to find critical points, where do critical points occur? Where the first derivative is 0. So my answer to this question is that I'm looking for x values where the first derivative is 0. Okay, so if I'm looking at, so that means that I want to look at the purple graph, right, because that's my first derivative. Am I looking for where it like flattens out? No. I'm literally looking for where the function value of the first derivative is 0. So that happens when the output value is 0. Okay, so the x coordinates are 5 and 15. Is everybody cool with that? Okay. So then, do I have to type that to be able to see what happens next? 5 and 15. Yay. Okay, so then inflection points. Okay, so what about inflection points? How do I look for those? So inflection points, potential inflection points, occur where the second derivative is 0. Okay, so where is the second derivative equal to 0? So now I want to look at the blue graph. The blue graph is 0. It looks like it could be 0 at 0, but it's kind of hard to tell. I think it's a little bit above it, but definitely at 10 and also at 20, right? However, in order to know for sure that you have an inflection point, the sign, S-I-G-N, of the second derivative has to change. So to the left of x equals 10, the second derivative is positive. To the right, it's negative. So the sign does change. So 10 is for sure an inflection point. Or, well, the x coordinate of an inflection point. Yes? 0, 0. What would make it not? If the blue graph did this. So it has a value of 0, but it doesn't change sign, right? Because it's to the left of 0, it's positive. To the right of 0, it's positive. Yeah. Well, so the point is that we can't know because we don't know what happens to the left of 0, right? And likewise for 20, we don't know what happens to the right of 20, so we can't know. So that gives us just the one value. Super cool. Okay, and then so find the intervals on which f is increasing and decreasing. So f is increasing on what interval? So what should we be looking for in order to say whether or not f is increasing, or sorry, decreasing? So the function is decreasing if it is a dirty word. The pink line. So the first derivative is below the x-axis, right? Because that would be where the first derivative is negative. So where is the first derivative negative? 0 to 5 and 15 to 20. Okay, so these are the last questions, right? There's no more after this? Oh, there's more. Jeez. Okay. So 0 to 5 and 15 to 20. And then f is increasing when the first derivative is positive. So that happens from 5 to 15. Okay, so up here. Okay. Notice that it doesn't matter that the first derivative is decreasing from 5 to 15. That has nothing to do with whether or not the function itself, f, is increasing or decreasing. Okay. We only care about the sign of the first derivative. So that was 0 to 5 and what? 15 to 20. And then from 5 to 15. Okay. How many more are after this? Okay. All right. So then, well, this is really good review though, because this brings everything together that we've talked about. This is an excellent problem. Okay. So, I have had people ask me, why do we use open interval notation instead of closed interval notation? Have you thought about it? Why do we do that? Yeah.
I don't know, but like, I got this question wrong because I entered it wrong. Like, I put 0 is less than x less than 5, and is less than x.
No, that's not interval notation.
Well, I mean, I understand it now, but
yeah. Okay. All right. But so my question is, why don't we include the 0 and the 5 or the 50? Because you said you use strictly less than and strictly greater than, right? When you. But why doesn't it? Why isn't f decreasing at 0, right? And why isn't it decreasing at 5? So the first derivative is 0, right? Neither positive nor negative. So how are we going to talk about whether or not it's increasing or decreasing at that point if the rate of change at that point is 0, right? Excellent. Okay, so then concavity. How do we figure out concavity? So your concave up if your first derivative is increasing or your second derivative is. So the definition of concave up is that your first derivative is increasing. What is that equivalent to saying? The second derivative is positive, right? Because saying that f prime is increasing is the same as saying the rate of change of f prime is positive, right? And notice if you look at these, okay, don't know how I'm going to get out of that, but okay. So, so the second derivative is positive where? From 0 till 10, right? So second derivative is above the x-axis from 0 to 10. And notice that corresponds precisely to where the first derivative is increasing, right? Purple curve is going up. Yes? Less steep, but still positive. Okay? All right, and then so for concave down, likewise, the second derivative is negative when it's below the x-axis, and correspondingly, the first derivative is decreasing, right? So, so if I come over here, concave up, that was 0 to 10, and then concave down was 10 to 20. Excellent. We are making progress, guys. Okay, so then, what happened? Oh, and so now we actually get to figure out what the graph is. Ha, sweet. Okay, so then they give us a starting value. They say f of 0 is 0. So that gives you a place to sort of put your pen when you start to graph, right? And then you use the rest of the information to coordinate, okay, is it increasing and concave up, or is it decreasing and concave up? Like, what happens from there? But you have a point to start at, and then you figure it out. So, yeah, I've already forgotten. So, okay, so we have to look back up here. So, between like 0 and 5. Okay, well, so remember, 5 was a critical value. And to the left of 5, our function is decreasing, and to the right of 5, our function is increasing. So that means at 5, we have a local, what? Is it a max or a min? Okay, right? Because you're decreasing, and then you're increasing. So it's either B or D. Sweet. Okay. And then let's see. So what's the difference between B and D? At 10, what's the difference between what goes on at 10 in each of these graphs? So in D, the point at 10 is a inflection point, right? Because to the left, it's concave up, and to the right, it's concave down. But in B, it's concave up and concave up. So at 10, there's no inflection point. But remember, we did all this work, and we found out there is an inflection point at 10. So that forces it to be D. Okay? Okay. So, cool. That's actually what I had planned to do, basically. So that was awesome. So just so it's on your screen somewhere at some point, this is, again, the final exam information, Tuesday, May 6th at 7. I think technically it's 7:10. Get there at 7, okay? And PSH 153. And test 3, we've moved up to next Thursday. So a week from tomorrow is test 3, and it's going to cover everything up to optimization, okay? So we're going to keep working on optimization today, and your homework for Friday is on optimization, but we'll probably start moving on to other material before the third test, so just try to keep up, but study up through optimization. Yes?
On the test, if there's going to be any like derivatives like we did with the master exam?
You have to be able to take derivatives to do all of the stuff that we're doing. Yeah.
I mean, like just like questions like in that master exam.
No, I'm not going to say find, you know, here's y, find y prime. That will not be on this test.
Will you give us, if we have to solve for volume
I'll think about it. I don't know. And then the test review has already been posted. So you have that already online to start working on, okay? So for next week's recitation, that means no quiz, but I'll probably have a handout that will help you gauge your study progress, and then you'll be able to work with each other to keep studying, okay? All right, so we're gonna do just a touch more sense making because I made pretty graphs. In particular, I guess I really just want to talk about this one. So this is the graph of what? What did I do? I have x equals tan of y. So it's the, oh, no? No idea? Oh, this is interesting. Yeah. This is the inverse tangent function, right? But I couldn't figure out how to type, arctan wasn't recognized in graphing calculator. So this was the way around it, okay? So this is arctan of x, but I just had to switch around the variables so that it would actually graph it, okay? But I picked this to talk about real fast because I did a terrible job of drawing what these middle boxes would look like. And I just want to make sure that I didn't give you the wrong impression, okay? So in particular, this is the type of curve that you should be imagining something looking like when the second derivative is 0. It's almost as if it were basically linear around the point where the second derivative is 0. Okay, so right, and we can do that. Whatchamacallit? We can do that by hand. So remember, so this is the same as saying y equals arctan of x. Okay, so this is the function that I've graphed. So what's its first derivative? One plus x squared. Okay. What's its second derivative? Give me a strategy. What are you thinking of in your brain? Yeah. Okay, so that's definitely one strategy. So then the rate of change would be -1, this thing, to the -2 times the rate of change of that thing, right? And so if I clean it up, I've got -2x over 1 plus x squared squared. Okay, so there's my formula for the second derivative. And so notice that the second derivative, if I wanted to find inflection points or possible inflection points, I would have to set this thing equal to 0. Question? You could also use the quotient rule if you wanted to. Yeah. So if I'm looking for potential inflection points, I have to set the second derivative equal to 0. So this is what that looks like, right? How do I solve something like this? Let me rephrase. If I have essentially a fraction equal to 0, what is the only way for that fraction to equal 0? If the denominator is 0? So if the denominator is 0, then I'm dividing by 0. That's bad. So if the numerator is 0, right? So solving this equation is equivalent to solving this equation, which is super easy. Okay, so here we found our potential location for an inflection point. Why do I say potential? Because we don't know if it actually is an inflection point until we check the sign of the second derivative, right? So I would have to plug in x values to the left of 0. So if I plug in an x value to the left of 0, notice that the denominator is something squared. So what does that mean about the sign of the denominator? It's always positive. So when I start plugging in values to check the sign of the second derivative, all I really have to check is what's going on in the numerator. So if I plug in a negative value, a negative times a negative is a positive, right? So over here, we're concave up, right? And that's definitely what the picture looks like, right? Concave up like a cup, right? And then if I plug in a positive x value, I've got a negative times a positive, so that's negative. So concave down over here. Okay? And so that's what we're seeing here in this curve. Okay? And so that means that at x equals 0, we really do have an inflection point. And so the thing that I was nervous that my drawing might have made you think is that I feel like I made it look like it had like a vertical tangent line when I drew it, and then that's not what it looks like. It looks more like this, where it's more of like a linear piece in the graph. Okay. Alrighty. So let me stop talking about that. And let's get back to that handout that I gave you guys. So for the sake of time, I feel like, how are you guys feeling about this? I feel like we just did a lot of practice that would help you in order to do this problem where I give you the function and you have to figure out sort of like how the accumulation function is changing. And then also this function where I ask you to figure out where maxes and mins occur. Do you feel like you can do those problems? Or should we do one of them? We should do one of them. Which one? First one? Okay. All right. So here's the problem. You have it on your paper. So the goal is for you to determine whatever values you need in order to talk about the behavior of the accumulation function. Okay. So what kinds of values tell you about the behavior of an accumulation function? The derivative, okay? So, well, first and foremost, it asks you to find the value of the accumulation function. So that's asking you to find what? G of x. Good. Okay, so that's the first set of values that you want to find. And then Arian said that the first derivative will give us some information about the behavior, okay? So that's probably another good thing to find. Anything else that'll inform us about the behavior? The second derivative. Wonderful. So go ahead and do that quickly. If you have your computer with you, graphing calculator will make this go really fast. Oh, I just busted my knee. Here's the thing though, the catch is if you do this in graphing calculator, I don't want you to actually graph it, right? The whole point is for us to pull the information about the graph using analytical tools. Once you find the values, what you do with them. All right, tell you what, you guys are taking a long time to find values. I'm gonna give them to you. I have faith that you can do this. Oh, I don't have 1.5 on my handout, do I? Okay. So these are the values. So I saw some people using graphing calculator, but I still didn't actually see anybody using it efficiently. Why did I say that graphing calculator would make this go really fast?
Set up the function, and then you just have to just give the name,
Uh-huh.
give the different inputs and that
Right.
will give you
Function notation. That's the key, right? So yes, graphing calculator will find the derivatives for you. That's not the quick and efficient part. This is not a difficult derivative to find, right? What graphing calculator does efficiently is allow you to use function notation to just substitute in values really fast to get the outputs. Okay, that's what's so helpful about graphing calculator in this part. Okay, but so let's talk about what do these numbers mean? So the function value is 3, the rate of change is -8, and the rate of change of the rate of change is 24. What does that tell me about the behavior of the function g around x equals 0? So the negative value means, the negative value for the first derivative means that g is decreasing. The positive value for the second derivative means that it's, when I say it, g is concave up. Okay, so decreasing and concave up looks like what? Oh, I'm seeing lots of stuff. What does it look like? Decreasing and concave up. Like a cup. Like the whole cup? No, half the cup. Okay, so something like that. Okay, Adam?
No, I know in my mind, like when I think of like the first derivative and I see those numbers, I can think of a picture.
Okay.
The second derivative, like when it just says 24,
Mm-hmm.
does that mean that it's like the steeper part of my concave up was at the bottom, or is that saying like it's trying to pull up like a steeper angle, or what is that saying?
So the rate of change is big positive. So it's increasing faster. So that means that the negative changes are getting smaller, faster. What would that be? I think that would be more of like a, where the steep part
As it comes to like 9 would mean it's starting to shallow, kind of still positive, but my change is getting a little less.
is decreasing at a slower rate. Okay. All right. So then at 1/2, what's going on? Oh, sorry. No. Okay. What's happening? We have a critical point, right? Because the first derivative is 0. Okay. So that means I potentially have a local extremum, right? So in order to decide if I actually have one, what do I look at? How could I tell if this is actually an extremum? So the second derivative is positive. What does that mean? So the graph is concave up and it pauses when x is 1/2. So that looks like this point right there. Right? So we have a local minimum. How are we doing, guys? I feel like energy is really low in the room right now. Are we following? Yeah? How'd I do what? So having a critical value tells me that the actual graph is going to sort of have a pause. So that looks like a horizontal tangent line at that x value. Okay, so the graph is going to look kind of flat-ish, right, nearby. And so if the graph is concave up at that value, though, that means that the derivative is increasing. So the only way for the derivative to be increasing and go through this value of 0 is if the derivative was negative to the left and then positive to the right. But that translates to the function itself decreasing to the left and increasing to the right. Does that make sense? Yes. Okay. So it is a dirty word. So if the rate of change is above the x-axis, then what does that tell you about the original function? So let's say, once again, that this is not this rate of change function, but let's say this is a rate of change function. Okay, so over here, the rate of change function is above the x-axis, right? What does that tell me about the original function? The original function is increasing because saying that r of x is above the x-axis is equivalent to saying it's positive. The y values, right? When you graph the rate function, its outputs are the y values, right? And so then all the rest of this graph, the r values are negative, so that means that the original function would be decreasing, right? Now there would be some sort of pause at that x value, but would there be an extremum? Is there a max or min on the original graph at this x value? No. Why? Because what doesn't change signs? The rate of change doesn't change sign, right? So the original function is decreasing and decreasing. So you don't have a maximum or a minimum. Yes. Mm-hmm. Yes. Yes. Okay. How are we doing? Shall we keep moving? Let's keep moving. All right. So then at x equals 1. So by the way, where is all of this happening? We haven't really been paying attention to the g values. But what do these g values tell you? all the action is happening in the first quadrant, right? So the y-intercept is 3, and then everything stays sort of up in the first quadrant after that. Okay. So then at x equals 1, the first derivative is 2, and the second derivative is 0. So the fact that it's 2 means that g is doing what? Increasing. That the second derivative is 0 means what? Possible inflection point. Okay. So in order to determine if it's actually an inflection point, you'd actually have to test some values nearby, right? So I tested, like I found the second derivative and I plugged in 0.9 because that's just to the left of 1. And I got that the second derivative was positive at 0.9. And then I plugged in 1.1 and I got that the second derivative was negative. So that means concavity does change, and it changes from being concave up to concave down at this point, but increasing the whole time. Okay, but I had to test other values in order to do that. Okay, so at 2, a similar sort of thing happens. There's not enough information here to really decide what's going on. We do know that the graph pauses, okay? But the fact that this is also 0 means that we would just need to investigate the values around it some more. I didn't do that, so I don't have a picture to show you, okay? But what you would do is you would test like 1.9 and 2.1 and see what happens nearby, okay? And then at x equals 3, we've got first derivative is 10, second derivative is 24. So what does that mean? Increasing, and the rate of change is also increasing, right? So what does that look like? Concave up. Give me a... Okay. Cool. You know, the other day I was talking to somebody, and because I've been teaching you guys like reversed for so long now, I was telling them how the left side of my body was all banged up in the bike accident. Because I'm so used to like, anyways. Thanks for that. Okay, so here's the deal. I really wanted to talk about this stuff today, and we didn't get to it, which means your homework is going to be really, really hard because we haven't practiced it. There are show me hows. So let me give you the rundown on how this works, right? So when you do applied optimization, that's a fancy way of saying you have to set up the equation, right? But once you set up the equation, the mathematics that you do doesn't change. And actually, like half of the problems I gave you, they already gave you the equation, right? So they'll give you an equation for profit and ask you to find how many products you have to produce to maximize your profit, right? And so the equation is already there. But in some cases, like this one, the equation is not there. And so it's like the related rates in the sense that you have to come up with the formulas. And usually what's going to happen is there's going to be a formula for the thing you want to maximize or minimize. And then there's going to be like a second equation relating the quantities involved so that you can rewrite that first formula that you're trying to maximize or minimize in terms of one variable, okay? So that's sort of the setup, okay? So you're usually, if you have to do a lot of work, the lot of work is write down the formula that you want to maximize or minimize. 9 times out of 10, it's going to be a formula of more than one variable. And for optimization, we haven't done that, right? So you're going to end up coming up with another equation that relates the quantities so that you can like do a substitution to rewrite this first equation in terms of one variable and do the optimization as we've been practicing, okay? All right. You'll try, right? And then we'll keep talking about it on Friday. All right. Have a good one.